Friends, today we shall continue our study of subsynchronous oscillations. We had developed the nonlinear and linear dynamic model of turbine generator shaft system. We have also analyzed the different torsional modes of oscillations and the mode shapes using model analysis. The major problems related to the torsional oscillations which we shall discuss today are the torsional interaction with power system controls, subsynchronous resonance and torsional fatigue due to network switching. As I pointed out in the beginning that the torsional oscillations may interact in an adverse manner with the power system network, and therefore, it is necessary to clearly understand the torsional interaction with power system controls, then subsynchronous resonance and torsional fatigue due to network switching. First, we will study about the torsional interaction with power system controls. When we talk about the power system controls, we will address the two important controls. One is the excitation control, that is interaction of the torsional oscillations with the excitation control, and second the interaction of the governor of the steam turbine with the torsional oscillations. Now, let us start with the interaction with excitation controls. Now, we have studied that power system stabilizers are used for damping the system modes of oscillations, that is the power system oscillations in the frequency range of 0.2 to 2 hertz. Now, here when we design the power system stabilizer, we ensure that a component of electrical torque or component of electrical torque produced is in phase with the speed deviation signal, and the parameters of the power system stabilizers are so chosen so that we get a component of air gap torque in phase with speed deviation, and this is a pure damping torque. Now, if you look here in the in this diagram, I have shown here the on x axis delta delta and on y axis delta omega, right. In case we produce a torque which is in phase with speed deviation delta omega, that is delta T e is the torque produced in phase with speed deviation delta omega, then this torque is a purely damping torque. Now, in practice what happens is that the speed signal is sensed by using a speed transducer, and when we mount a speed transducer say a particular location, let us say at the generator end of the turbine generator shaft, then at that particular location the speed signal has a high component of the torsional oscillations. If you examine this diagram, that is for a typical turbine generator system, this is the mode shape corresponding to 16.3 hertz, and we can easily see here that the component of speed deviation signal which is sensed at the generator end of the shaft is quite a large one, and this component when it is processed through the power system stabilizer will produce air gap torque, a component of air gap torque which will have a large phase shift between the speed deviation signal and the air gap torque produced. For example, if you see in this diagram, in the typical case the air gap torque or a component of air gap torque produced due to torsional component which is actually fed back through the power system stabilizer. That is, the speed signal has a torsional component or high magnitude of torsional component, and this signal when it is fed through the power system stabilizer and the air gap torque which is produced, this air gap torque comes out in the fourth quadrant, a typical case. Now, this air gap torque delta T e, when it is resolved into two components, one in phase with angle deviation, the delta delta, another in quadrature with angle deviation, that is in phase with speed deviation signal delta omega. Now, the component of the air gap torque in phase with speed deviation comes out to be negative, that is the power system stabilizer will contribute a negative damping torque, and this negative damping torque, if it is more than the normally existing system damping, then it will cause excitation of the torsional modes, because as we have seen that the damping of the torsal modes is very low, right, and the moment you have a large negative damping torque produced due to the power system stabilizer, then the net damping may become negative and the torsional oscillations may grow in magnitude, and therefore, there is a necessity to account for this adverse effect when we design our system. Now, various measures have been suggested to counteract this problem of excitation of torsal modes due to power system stabilizers. One very interesting example is given in the power system stability and control by Kundur in the textbook Power System Stability and Control by P. Kundur. An example 15.2 addresses the various aspects of the interaction of torsional oscillations with excitation control. Now, to examine this, he has considered a steam turbine which has high pressure section, then there are three sections which are called low pressure sections. He names them as LP1, LP2, LP3, and each low pressure section has two sub sections called left and right, and they are all mounted on the same shaft. At the end is a generator. Now, to overcome the problem of excitation of torsional modes due to adverse interaction between the excitation control and torsional oscillations, the studies were conducted by putting speed sensing device at the end of the generator. That is, suppose you put speed sensing device here, the speed sense is at delta omega g. Another location which was identified for sensing the speed is between LP2 and LP3, that is delta omega c, that is at this location C. Now, at C forms a coupling between the LP2 and LP3 sections. Similarly, studies were also carried out by sensing speed at the coupling between LP1 and LP2. The reason for trying these different locations were that at these locations the amplitude of the torsional oscillations was very small, right. Therefore, if you pick up the speed here, then the chances of excitation of torsional modes is practically low. Another step which was taken is that a filter was put in the power system stabilizer circuit. That is, the speed deviation signal is first filtered out by putting a special filter which will filter out or eliminate the torsional modes, right. Now, in case actually the torsional mode 1 is having the predominant signal, then the filter is designed so that the torsional mode 1 is completely attenuated, while other torsional modes will be highly attenuated, right. And the first step which was taken was that study was conducted considering delta omega PSS by locating this PSS at different locations. Studies were conducted by putting the speed sensing or speed sensor at location B, at location C, and then at B and C both, right. Then the next stage, the studies were conducted by putting delta omega PSS with a torsional filter, right. Then the last study was carried out by putting a stabilizer where we do not sense the speed deviation as the input signal, but we sense the deviation in power as the input signal, this delta P stabilization. And studies show that if you have delta omega PSS only without torsional filter, then as you increase the power system stabilizer gain, then some of the torsional modes will get excited or they will have negative damping. Then further studies were carried out when the torsional filter was put, then it is seen actually that the moment you have torsional filter incorporated, then the chances of excitation of torsional modes is eliminated. Further, when the delta P stabilization was put, then the results obtained were similar to what we got actually in second case, where delta omega PSS with a torsional filter was put. Now, all the details are given in the example 15.2. I will suggest the interested readers to go through this example in detail. The next aspect we have to address is the interaction with speed governors. How the speed governors will interact with the torsional oscillations. Now, historically, the interaction with speed governors was observed or experienced in 1983 when a 635 MVA 1800 RPM nuclear unit at Ontario Hydro was commissioned. This unit, which is a nuclear unit, basically the turbine is similar to a steam turbine. It is a steam turbine only, okay. And the difference in this unit was that it was equipped with a fast acting electro hydraulic governor system, because we may have the mechanical control system, right, and we may have a fast acting electro hydraulic governor system. In this electro hydraulic governor systems, which are now provided in most of the modern turbines, the low power functions are performed by using electronic circuits, that is the speed sensing and certain processing is done using electronic circuit. One of the important processing which is done in electro hydraulic governor system is they use a linearizing circuit to compensate for the non-linear flow versus valve position characteristic of the steam valves. That is, if you plot a characteristic which relates the steam valve position with respect to the steam flow, then this characteristic is a very linear characteristic, non-linear characteristic. And to compensate for this non-linear characteristic, right, we provide here a electronic linearizing circuit. Then it was observed that when this machine which was under commission, when this machine was loaded to 100 megawatt load, its capacity is 635 MVA, then the vibrations of the steam valves was observed, experienced, and then immediately they looked into the electronic circuits and some retuning of the electronic circuit was done. With that retuning, they could load up to 475 megawatt, and at that particular loading condition again it was seen that the steam valves were vibrating, and then when it was examined in detail, it was found that this nonlinear, that is the electronic linearizing circuit, right, it was behaving in a different fashion at that particular frequency. That is, a particular frequency was sensed, because here the governor senses the speed of the rotor, and for sensing the speed of the rotor, the speed sensor is mounted on the high pressure end of the steam turbine. Okay. And at that particular end, it picks up the various torsional components, right, and when these torsional components are processed through the electronic circuit, it was found that the speed drop at 475 megawatt loading came out to be something like 12 times more than the normal 4% speed drop, and then certain action was taken to overcome this problem or to mitigate this problem. Therefore, this is also a very serious problem when you have to address the torsional interaction with the governor circuits, because modern steam turbines are equipped with electro-hydraulic governors, and these days these circuits are so designed so that all through the loading condition a 4% speed drop is maintained. Speed drop, you know, all the speed drop parameter R, which is the governor characteristic, where actually the when you change the load from no load to full load, the drop in speed is 4% from the normal value, or when the machine is operating under full load condition and if the load is thrown off, the increase in speed will be 4% of the rated speed. Now, this particular problem has been nicely dealt with in the research paper written by D.C. Lee, R.E. Beaulieu and Rogers, effect of governor characteristics on turbo generator shaft torsionals. This is a specific problem which was examined. This has appeared in 1985. In fact, these torsional oscillations do interact adversely with the nearby HVDC controls also. This needs to be examined in detail, but it is observed that the HVDC controls also interact in an adverse manner if you do not account for the torsional modes. The next important aspect we basically study is the subsynchronous resonance. First, let us define what we mean by the subsynchronous resonance, then we will study this phenomena in detail. The subsynchronous resonance is defined as an electric power system condition. That is, subsynchronous resonance is an electric power system condition where the electric network exchanges energy at one or more of natural frequencies of the combined system below the synchronous frequency of the system. That is, here the importance is that the frequencies of interest are the frequencies which are less than the synchronous frequency. These are called the subsynchronous frequency, and there is a condition where the electric network, that is the power system network, exchanges energy at one or more of natural frequencies, right. And therefore, to understand this problem we have to examine the system very carefully, and let us understand the SSR phenomena or subsynchronous resonance phenomena. This SSR phenomena was first experienced in 1970, resulting in the failure of turbine generator shaft at Mojave plant in Southern California. Now, till that time people had no idea about the subsynchronous resonance, and in the Mojave plant, which is located in Southern California in USA, right, in 1970 the shaft of one machine completely damaged. Then the second shaft failure occurred in 1971. Then it was a serious problem. The studies were conducted, the system was modeled, and after detailed studies it was found that these shafts were damaged because of SSR phenomena which occurred in the system. This SSR phenomena primarily occurs in series compensated transmission lines. Okay. Now, there is a necessity for us first to understand the characteristic of the series compensated transmission lines before we understand the SSR and its impact on the system. Now, first let me just tell you that suppose you have a uncompensated transmission system, and in uncompensated transmission system suppose fault occurs in the transmission line. Okay. Then depending upon the instant in the voltage wave at which the fault occurs, there exists a decaying DC component of fault current, and this decaying DC component of fault current flows through the distributed stator windings of the system. That is, when the stator windings, which are distributed 3-phase stator winding, right, it will carry the decaying DC component of the fault current. And when this decaying DC component of fault current is flowing in the stator winding, then an air gap torque having frequency equal to 60 hertz will be produced. Right. Now, normally under steady state condition, the torque which acts on the rotor of the turbine generator system or is always having 0 frequency. It is a unidirectional torque when it is carrying 3-phase balanced currents. But the moment actually the stator carries a decaying DC component of current, right, the torque or air gap torque is produced with its frequency is 60 hertz, if it is a 60 hertz system. If it is a 50 hertz system, the frequency will be of 50 hertz. Similarly, when you know that whenever there is unbalanced fault which takes place on the uncompensated system, then the negative sequence currents will flow in the stator winding of the generator, and these negative sequence currents will produce the air gap torque whose frequency will be 2 times the system frequency. It is a 50 hertz system, the frequency will be 100 hertz. If it is a 60 hertz system, it is 120 hertz. And therefore, there is a necessity that when you design your turbine generator shaft, none of the torsional modes should be close to 60 hertz or 120 hertz. Further, if I consider now a series compensated transmission line, and the primary purpose of providing series compensation is to reduce the line impedance, so that we can transfer more power on the transmission line. Now, let us consider a machine infinite bus system where we have a generator, a transformer, a step up transformer, and the transmission line whose parameters are Re and Xe. The resistance is Re, reactance is X. Now, we have provided a series capacitor of reactance Xc, right. Now, this system when a fault occurs in this particular series compensated system, then the fault currents will also have components of frequency which will be corresponding to the natural frequency of the inductance and capacitance of the system. Now, you all know actually that suppose when you have RLC circuit, when this RLC circuit is excited, right, then the current which flows will have a frequency of oscillation which depends upon the inductance and capacitance of the circuit. Now, since the capacitance which you put here in the circuit is to partially compensate for the line reactance at power frequency, and therefore, at a frequency less than the power frequency at sub synchronous frequency, these two reactances may become equal, right, and at that time we say that it is a series resonance occurs. Now, we can draw the equivalent circuit of the system, that is generator can be represented by a voltage in series with the reactance, transformer with reactance x t, line with reactance R e x e and resistance R e, capacitance x e. This can be simplified and we can write down a voltage source in series with the resistance, the total reactance x L which is x e plus x t plus x double prime subtangent reactance, and a capacitance connected to infinite bus. Okay. Now, for this circuit, the natural frequency of oscillation, we denote it by the symbol omega n, is equal to 1 divided by square root of L C. This is natural frequency of oscillations. Okay. This can be written as omega naught divided by square root of omega naught into L omega naught into C. Okay. This is exactly same as this one, that is you have multiplied and divided by omega naught. This can be expressed as omega naught multiplied by square root of x e by x L. Okay. Therefore, now we have a relationship between the natural frequency of oscillation f n with the system frequency f o and the values of the line reactance and series capacitor, the reactance of the series capacitor. Now, this relationship is a very important one. Now, the problem comes something like this, that whenever some disturbance takes place, right, and if the currents of this frequency f n flows in the stator winding of the synchronous generator, then there will be a torque developed in the air gap, we call it air gap torque. The frequency of this air gap torque will be equal to F o minus F n. That is, if F n is the frequency of the currents which are flowing in the stator winding, then the frequency of the torque developed or frequency of the air gap torque developed due to this current will be F o minus F n, because we have seen that if F n is 0, that is if it is carrying DC current, decaying DC current, the frequency of the torque developed is simply F o, right. Therefore, now if the current flowing has a frequency F n, then the air gap torque will have a frequency which is F o minus F n. Now, in case the frequency of the torque developed, that is F o minus F n, if it coincides with any of the torsional modes, then these torsional modes can grow in magnitude or can be sustained. That is what is the main philosophy of excitation of torsional modes. This table is an important table which shows the percent compensation, that is x e by x L, this ratio multiplied by 100, that shows the degree of compensation. For example, here when I say 10, this is the 10% of the line reactance is compensated, and so on, as on this 10, 25, 30, 45 and 50 as these frequencies. With this compensation, the natural frequency of oscillation comes out to be 18 hertz, 30 hertz, 32.6 hertz, 38 and 42.4 hertz. While the slip frequency we saw at f 60 minus Fn, right, because when the currents of this natural frequency flows in the stator winding, then the torque developed will have a frequency of 60 minus Fn, that is the slip frequency. Slip frequency torques are produced, and this slip frequency torque should not have should not coincide with the frequency of any of the torsional modes. This is one of the important requirements. Now, you can easily see here actually that at low when the compensation is low, the slip frequency is high, right, and as the compensation increases, the slip frequency decreases. Suppose you go 50% compensation, this frequency may come very close to frequency of mode 1, right, and as you decrease this, you will find that it will go and match with the higher and higher slip frequency, and it may match with higher modes. A series capacitor compensated transmission network can cause sustained or negatively damped subsynchronous oscillations by two distinctive mechanisms. Now, here very important aspect which we will address in our study, that is a series capacitor compensated transmission network can cause sustained, I am using the word sustained or negative damped subsynchronous oscillations. There are two mechanisms. One is the self excitation due to induction generator effect, and second is interactions with torsional oscillations. Now, these two effects are completely different. Now, to understand this, the self excitation due to induction generator effect, we can visualize that a synchronous generator whose rotor is running at synchronous speed. When the stator of the synchronous generator is carrying subsynchronous frequency currents, right, then due to the subsynchronous frequency currents, a rotating magnetic field is produced whose speed will be less than the synchronous speed, while rotor is rotating at synchronous speed. This is a situation similar to induction generator effect. That is, if we consider only the situation where the stator is carrying subsynchronous currents, right, and then the behavior of this synchronous generator can be examined considering the induction generator effect, because the induction generator, the rotor of the generator rotates at a speed higher than the synchronous speed. Now, when you examine this, the self excitation due to induction generator effect, let us look at the equivalent circuit of the synchronous generator when it is behaving like a induction generator, right. We are not considering the synchronous generator aspect here, we are considering only that portion of the system which behaves like induction generator. This is the armature resistance, this is the leakage reactance, this is the resistance of the rotor, this is the leakage reactance of the rotor, and this is the resistance which takes care of the loading, that is the load. Now, here this resistance R is 1 minus S by S. Now, the slip is equal to Fn, the frequency of the current which is flowing through the stator, minus Fo, the frequency corresponding to the synchronous speed. Then Fn minus Fo divided by Fn is the slip, because when we define the slip, right, what we do, we suppose it is a induction motor, right, the suppose actual speed is n, then the synchronous speed is ns, then the slip is ns minus n, and then this is expressed in percentage of ns, Okay. Now, here corresponding to this Ns, I am using this frequency Fn, because the current which is flowing is natural frequency current Fn, that is Fn minus Fo by. Now, since Fn is less than Fo, the slip is negative. When the slip is negative, then this quantity, this part of the resistance will become negative, because S is negative in the denominator, right, with 1 plus this becomes positive, but there is a negative term here, this resistance becomes negative. Now, when if we neglect this magnetizing reactance, then equivalent circuit can be shown as R effective plus X effective. This is the equivalent circuit looking into the stator terminals of the synchronous generator. That is, when look into the stator terminals, then this circuit or stator circuit will behave as if it has a effective resistance and effective reactance. Therefore, the net effective resistance is equal to R A plus R R by S, and now S is negative, right, and therefore, in case R R by S when exceeds R A, then R effective becomes negative. Now, the point here is that we have, when we look at the stator side only, the stator is connected to the transmission network through transformer, and it is a series compensated line. Now, in case the currents of a natural frequency Fn flow in the stator winding, right, and if the circuit has net resistance which is less than 0 or negative resistance, then these oscillations can grow. That is, the in RLC circuit, if R is positive, then the oscillations will damp out, okay, they will decay, but if R becomes 0, the oscillations will sustain, but when R is negative, oscillations will grow, right. And this is the phenomena where we say actually that due to the series compensated transmission line, right, and due to induction generator effect, the effective resistance of the circuit as a whole will become negative or or 0, then the oscillations can either grow or get sustained, right. And when these oscillations are sustained, right, their magnitudes are increasing, then there will be torques developed on the generator of corresponding to the slip frequency. And as I told you that this torques should not have a frequency which should match with any of the torsional modes, we want to avoid the damage to the system. The another aspect which I have to emphasize here is the torsional interaction resulting in SSR. Now, as I told you that so far the induction generator effect is concerned, there is no interaction with the torsional modes, right, and this phenomena is basically a circuit phenomena. When we talk about the torsional interaction resulting in SSR, now if the complement of the natural frequency, when I am using the word complement, that is the synchronous frequency minus the natural frequency of the network is close to one of the torsional frequencies of the turbine generator shaft system, torsional oscillations can be excited. This is what we have already seen. This condition is referred to as subsynchronous resonance. That is, in case the complementary frequency, we always call the word complementary frequency, because the slip frequency plus the natural frequency, the sum is equal to the system frequency, equal to the complementary frequency. In case the complement of natural frequency is closer to any of the torsional modes, right, then the oscillations can be excited, and this phenomena is called SSR phenomena. The consequences of the subsynchronous resonance can be dangerous. If the torsional oscillations built up, the turbine generator shaft will break with disaster consequences. As you have seen actually that at Mojave the shaft damage took place, and it was ultimately identified due to the occurrence of SSR phenomena. Even if the oscillations are not unstable, I am using the word now, oscillations may be stable or unstable. System disturbances can result in sharp torques of high magnitudes, causing loss of fatigue life of the shaft. The idea here is that when the oscillations are produced in this shaft, okay, even if suppose the oscillations do not grow, right, the shaft is subjected to increasing and decreasing stresses, right, and due to this there is certain fatigue caused to the shaft, and there is a terminology which is used is called the fatigue life. That is, each shaft has some fatigue life, right, and when this shaft is subjected to this oscillatory torques, the fatigue life is lost or it decreased. Now, another important aspect is very important, the torsional interactions affects or the torsional interaction affects involve energy interchange between the generator shaft system and inductance of the capacitances of the network. That is basically there is a exchange of energy between the generator shaft system and the network inductance and capacitance, because they are the energy storing devices. Therefore, the analysis of SSR problem requires representation of both the electromechanical dynamics of the generating units and electromagnetic dynamics of the transmission network. This point I want to highlight, because when we studied the power system dynamics, okay, and when we developed the synchronous generator model, we neglected the stator transients, right. The stator circuit is represented by algebraic equations, okay, and similarly the transmission line equations are also obtained by steady state analysis, or transmission line performance is also obtained through algebraic equations. It means, we have not represented the dynamics of the transmission line network or transmission network or the stator network. But here when we want to analyze the torsional interaction, then we have to develop detailed dynamic model of the electromechanical system as well as the electromagnetic dynamics of the transmission network. And that is why whenever you develop the model, the dimension of the model will become higher, right, and a lot of research work has been done on modeling the system for analyzing the SSR phenomena. The generator stator circuits and the network cannot be represented by steady state algebraic equations as in the system stability studies, which is now I have highlighted. Consequently, the system model used for SSR studies is of higher order and greater stiffness than the model used for stability study. Is it clear? That is, when I say that when you develop the model of the system for SSR study, the dimension of the model is high. It is a high order dynamic model of the system. And since we know about the stiffness, what we mean by the stiffness, that is the smallest eigenvalue to the largest eigenvalue, that this ratio gives us the stiffness. Therefore, since actually there will be different type of time constants involved, the stiffness also is different, greater stiffness is there, and therefore, when you solve these equations, you may have to take small integration step. Now, several techniques have been used to analyze the SSR phenomena. I will just briefly discuss these techniques. Out of all the techniques, the simplest technique is eigenvalue analysis, where you develop the linear dynamic model of the system and obtain the eigenvalues of the system, and you perform the studies whether the system is stable or not stable, and which are the modes which may get excited depending upon the dampings associated with or damping ratios of various modes of oscillations. That is, when you consider the realistic system, right, then the eigenvalues will be complex conjugate or real, right, and we can find out the damping ratios associated with each of the modes, and we can find out what is the damping associated with this in case damping is poor, or if it gets excited, if damping is negative, then one has to take some measure. The second method is called frequency scanning method. This method is used actually to do some preliminary studies. What is done is that looking from the internal bus of the synchronous generator, right, you try to see what are the frequency of the various components. That is, you can try to find out the impedance of the network to different frequencies, right, and that helps us actually in finding out which helps us in finding out preliminary the occurrence of SSR phenomena, because we can easily find out actually what is the impedance to this particular frequency, what is the impedance to the next frequency, called frequency scanning, right. Wherever the impedance is very low to particular frequency, that is the cause for concern. Another is the frequency response analysis for full system. That is, we can find out the stability of the subsynchronous modes by applying the multidimensional Nyquist criteria for this particular system. This is a completely a frequency domain analysis for analyzing the stability of the subsynchronous modes. Then we also have one simple technique called frequency domain analysis, but this technique is little bit approximate as compared to the frequency response analysis. However, the most efficient technique is time domain analysis. That is, we can perform and obtain the time domain solution or response of the system using EMTP program. In this, you can model the 3-phase system, you can model the non-linearities of the system, and the complete transient behavior can be studied applying the EMTP program, or today we are using the EMTDC or PSCAD program, right. These programs are very useful in analyzing the SSR phenomena, and IEEE has given 2 standard models for studying the SSR phenomena. One is called the first benchmark model, and second is the second benchmark model. Then we have come to a very important aspect, that okay, if suppose SSR problem takes place, then we have to take some countermeasures to eliminate the SSR problems. The various techniques have been reported to mitigate this SSR problem. Some of the methods for or countermeasures are static filter, dynamic filter, dynamic stabilizer, excitation system damper, protective relays, and NGH scheme. In the static filter, the basic approach is that we put in series with the stator winding a circuit which is having parallel resonance to a particular torsional mode, so that the stator circuit will not carry frequency or current of subsynchronous frequency. That is, if this parallel network is tuned for some subsynchronous frequency, right, then no currents can circulate in the stator circuit of that particular subsynchronous frequency, and therefore you can mitigate this problem. Another is the dynamic filter. In this dynamic filter, again we inject a voltage in series with the stator circuit, which will be equal and opposite to the subsynchronous voltage which is generated in the stator winding. So, that we nullify the voltage which is developed in the stator winding of subsynchronous frequency. So, that no currents of subsynchronous frequency will flow. This dynamic stabilizer is basically a shunt connected device, right, and it is a thyristor control. By appropriately controlling this reactors by switching on and off the thyristors, this SSR problem can also be overcome. Again, excitation system damper. Now, we have the power system stabilizer. Similarly, you can design a stabilizer, right, to damp the SSR problem, because power system stabilizer is designed to take care of low frequency, that is 0.2 to 2 hertz, and therefore, if you want to use this PSS or excitation system damper, then it is designed for those torsional modes of oscillations, right. The protective relays are designed so that as and when this SSR problem is sensed, the relays will disconnect the system from the supply. That is, the machine before it gets damaged, it is disconnected. This is what is the meaning of the protective relays. They will sense the subsynchronous phenomena and then disconnect the machine. The last scheme is NGH scheme. This NGH scheme, N stands for Narayan G. Hingorani. This is the first person, this is the person who is the father of FACS technology, and he has suggested a scheme for mitigating the SSR problem. Here again the approach is very simple. Across the series capacitor, a thyristor control resistor is connected. There is across, there is a shunt resistance which is controlled by switching on and off the thyristors, right. And as we know actually that whenever the subsynchronous frequency currents flow, the voltage across the capacitor will become non-sinusoidal, and the period of this voltage wave will be less than 180 degrees or more than 180 degrees. Therefore, this NGH scheme senses the period of the voltage wave which is developed across this capacitor, and it will short circuit the capacitor in case period is more than this. So, that energy corresponding to the subsynchronous frequencies will be dissipated, and that way it will be ensured that the voltage across the capacitor remains more or less sinusoidal. If the voltage across the capacitor is sinusoidal, then no current will be of subsynchronous frequency. This is what is the philosophy, and students have done projects using NGH scheme. The last aspect which we should address is the impact of network switching disturbances. Now, this is a very important aspect. I will just tell you that in any power system, we have number of switching phenomena. Switching phenomena are planned or unplanned. Planned phenomena means, suppose I want to switch off a transmission line, this is a plan, okay. But unplanned means the faults, occurrence of the faults, clearance of the fault, reclosure of the lines, right. Now, all these switching phenomena will cause a sudden change in the electrical power output of the generator. Suppose there is a transmission line which is supplying some say power, okay, and if this line is switched off, the electrical power output will become suddenly 0, right. And because of sudden change in the electrical power output, the shaft of the synchronous generator is subjected to stresses, and that causes the loss of fatigue life, right. And therefore, this subject is a detailed subject of importance, and that is why number of, you can say, studies have been conducted so that the fatigue, loss of fatigue life due to switching phenomena is reduced. Now, next point is the hydro generator torsional characteristic. Till now whatsoever I had talked is the torsional characteristics of steam turbine generator. The rotor of the hydraulic generating unit consists of a turbine runner and a generator rotor. If the unit has a shaft driven exciter there is an additional rotor mass. Consequently, there are at most two torsional modes of frequencies, that is generator, runner, that is the hydro turbine, and exciter. Therefore, there cannot be more than two modes of torsional oscillations. The inertia of the generator rotor is about 10 to 40 times higher than that of the turbine, runner or water wheel. The torsional natural frequencies lie in the range of 6 to 26 hertz. That is because of vast difference in the inertia constants, the torsional frequencies are in this range 6 to 26 hertz for typical, this is a typical range. There are no reported causes of adverse dynamic interaction between the hydro generator rotor and the electrical network. Now, there are two principal reasons of no adverse interaction. One is the high value of generator rotor inertia in relation to the inertias of the turbine, runner and exciter rotor. This effectively shields the rotor mechanical system. As a result, it is difficult to excite torsional oscillations through disturbances on the generator. That is, whenever some disturbance takes place in the generator, these oscillations are not excited. The last one is that the runner is moving in a water, and therefore, there exists a good damping, this viscous water wheel damping. This makes the inherent damping of the torsional oscillations for two hydro units significantly higher than the steam turbine generators. Right? You understand this point, that in the steam turbine, the turbine blades are moving in the steam. Here it is moving in water, therefore, there is a lot of viscous friction, right, and therefore, the damping is very high. Now, let me conclude here that today we have studied the interaction or the torsional interaction between the system control, the excitation system control, governor control. We also studied the SSR phenomena. We also studied the techniques for analysis of SSR phenomena and countermeasures for overcoming the SSR problem. We have also studied that this SSR problem does not exist in hydro turbines. Thank you.